All right, are we ready? Everyone, I think we're ready. All right, everybody, we're ready to start. So, AV, are you guys ready? All right. So, welcome to ShmooCon 2016. We're going to start the talks, and the first one is Breaking Bulbs Briskly by Bogus Broadcasts.
Good afternoon, ShmooCon. Welcome to Breaking Bulbs Briskly by Bogus Broadcast. First, I'd like to thank the Shmoo Group for allowing us the opportunity to talk to you guys. We really do appreciate it. So, my name is Joe.
And I'm Ben.
And today we'd like to make available some tools for conducting reconnaissance against ZWave networks, as well as discuss exploiting wireless automation systems in order to break fluorescent bulbs in a rather quick manner. So what you see there in the animation is just the hardware components that go along with the software tools that we'll be talking about later. In particular, some HackRF1 software-defined radios, some ZWave devices, and some fluorescent bulbs. So let me start with just some basic information about ZWave for those that might not be familiar. It is a proprietary low-rate wireless network protocol that operates in the 900 megahertz spectrum. Even if you're not familiar with the protocol, you probably come across ZWave devices every day. You might not even realize it. There are several hundred companies out there that either manufacture or sell ZWave-capable smart devices. And the bread and butter for this protocol right now is really the home automation and security systems. Now, with over 35 million devices sold, ZWave has a fairly large market share. Ranging from devices as simple as smart plugs and light bulbs to a little bit more complicated devices like door locks and environmental sensors like smoke detectors, PIR sensors, and then even more physically robust devices like automated water valves with leak detection and smart energy meters. Now, Ben here has been doing security research on a similar wireless protocol called ZigBee for quite a while now. And when I started working for him not too long ago, he said, Joe, we've already figured out quite a bit about ZigBee. I want you to go do some research on the security of this proprietary ZWave protocol. I said, sure thing, boss, whatever you want. So like a good security researcher, the first thing I do is I start looking for what tools are already out there. Nobody really wants to recreate the wheel. That takes way too much time. However, since the protocol is proprietary, requires signing an NDA in order to get your hands on the software development kit, I found that there wasn't very much out there. So first, there's a open source project called ZWave, which provides software libraries for interacting with a ZWave USB stick. This is great if you want to develop your own automation software, but it doesn't really allow you to operate outside the bounds of the protocol, which is really what a lot of security research is about. So I decided to just move on, and I found that there's a tool called Z-Force that was presented at Black Hat 2013. Seemed really promising, other than the closed source nature of the custom firmware and the software to go along with it. For this presentation, they talked about using this Texas Instruments transceiver in order to exploit a implementation flaw in the key exchange program or protocol of one particular ZWave door lock in order to reset the shared private key and get unauthorized access to the door and then being able to control the door lock. So it seemed really promising. However, when we were unable to replicate the functionality of this tool, which was awesome, and when we started asking questions of the developer, the tool was taken down, of course. So instead of trying to beat my head to figure out how to force this tool to work for my needs, I just decided to move on. And I found another tool called Scapy Radio, again presented at Black Hat. So this isn't really a ZWave tool. It's more of a framework that allows you to build your own wireless sniffer and injector on top of the Scapy Radio framework. It uses the well-known Scapy packet manipulation framework that I'm sure many of us in this audience are familiar with. And then it also uses the capabilities to control software-defined radios of GNU Radio, which is a much more specialized skill set. Even better, for this presentation, the guys implemented a basic support for the ZWave protocol in order to demonstrate a packet replay attack. So awesome. So while there's not really a robust set of ZWave exploitation tools on par with, say, the Killer B framework for Zigbee, for those that are familiar with that, there was at least a foundation that allowed me to start playing with ZWave devices. And that's what we're here for today. We wanted to make available a tool that collectively I call EasyWave. It is built on top of Scapy Radio with extended support for the ZWave protocol. For Scapy Radio, for their presentation, they did a basics implementation of the ZWave protocol that has 3 command classes, which are groups of device functionality. We extended that to a total of 33 so that we can do more stuff with ZWave devices. So now EasyWave includes 3 standalone tools. The first one is called Easy Stumbler. Yes, it's named after ZB Stumbler from the Killer B framework, again from Zigbee. So Easy Stumbler does network discovery and enumeration. Next we have Easy Recon, which interrogates individual devices on a ZWave network in order to solicit the information you see listed there, which just happens to be information that would really be useful to a security researcher who's trying to figure out if there's actually any security in ZWave at all, which was, of course, my job at the time. And then finally we have Easy Fingerprint, which exploits differences in transceiver design in order to distinguish between different generation ZWave modules embedded within the target device. It does this by manipulating the physical layer preamble in such a way that the older generation ZWave module is able to receive transmissions and respond, whereas the newer generation ZWave module is not able to synchronize with the physical layer frame and therefore can't respond, and that allows us to determine what generation module we're dealing with. So one limitation that I'd like to bring up at this point is if the target device is using encryption, the tool is not able to get the current state or the configuration settings of the target device. But it's still everything listed there is still fair game. Since I brought up encryption, and because we had a really spirited discussion with a particular device manufacturer just last week, just wanted to give a quick note about security within the ZWave protocol. So the protocol does support AES-128, awesome, but it's completely left to the individual device manufacturers in order to use it in each of their devices. So again, like a good security researcher, I wanted to find out how often encryption is actually used in ZWave devices. So we went out, we purchased 33 popular ZWave devices available today on the market. We found that only 9 of them actually support encryption. So out of those 9, 5 of them were door locks. You'd hope that all door locks would, or all wirelessly controlled door locks would use some form of encryption, where they're not really locks at all. And then the other 4 devices were some of the newest devices currently available on the consumer market. An interesting note about those 4, however, is that 3 of them used opt-in security. Now, what I mean by that is you see a picture there of one of the device's user manuals. So the user manual, the instructions in the user manual have the user add the device in a non-secure mode. And then buried towards the end of the user manual is a little snippet that says, hey, if you guys want to use the secure mode of this device, add it to your network in this way, instead of the way we already told you. Well, who reads that far in a device manual, especially when you've already added it to your network and it's already working? So the story here is that while yes, the protocol supports encryption, many of the devices currently available don't, and the ones that do, it's not always used by default. So now I'd like to just give you a quick demonstration of the tool. So what we have here is 2 HackRF1 software-defined radios. One is used for transmit, one is used for receive because they're not full duplex. Of course, you can change this out with whatever other software-defined radio you want to, as long as it's compatible with GNU Radio. We chose them because they're fairly cheap compared to something like a USRP. Over here, I have a small ZWave network with just a couple devices for the demonstration. And then over here is the lamp that I stole out of my room, just for you guys. And it is connected to another ZWave device down here that you can't really see because of the power cords. So for time's sake, I'm going to skip the network discovery portion because it really is just passive scanning until traffic is observed and a unique network identifier is found, which is called the home ID for ZWave. And we're just going to skip ahead to the network enumeration. So like I said, I've got a small network up here already. I'm going to run EasyStumbler using the home ID that we assume that we found through passive scanning. So what's going on right now is we are sending out broadcast messages that solicit compulsory acknowledgments from all the devices on the ZWave network that are within range of the software-defined radio. So when those devices acknowledge that message, they're making their presence known, and you see them pop up on the screen there. In a second here, the scan will finish with a little report. Okay, so you see the scan found a total of 5 ZWave devices on this network. So now that we have the devices on this network, let's go ahead and interrogate one of them. So the first one I'm going to do is a device that's not configured with encryption at the moment. Now the node ID from the previous scan, that's akin to the IP address on the local network for this protocol. So I'm going to scan device number 3 or interrogate device number 3. What's going on right now is I'm sending out a host of messages requesting specific information from the device. Because there's no source authentication in the ZWave protocol when encryption is not used, the device is going to happily oblige and send that information back to me. And then the tool is going to convert that into a human-readable format, as you can see there on the screen. So the device that we just scanned, you can see is an AOTech Smart Switch 6. Below that, you can see all the software and firmware version information, and followed by a list of all the functionality of this device. And then there at the bottom, you see the basic status of the device, which is currently off. We skipped scanning the configuration settings because that takes more time than what we have for this presentation, but I think you get the idea. So now, just in case you're curious and to make a particular manufacturer a little bit happier, we're going to interrogate a device that is currently set up with encryption right now, just so that you can see the difference. So again, it's going to send the same stream of requests to this device, asking for its specific information, and you'll see it pop up here in a second. All right, so you can see that this device, we still get the information about the manufacturer. We see that it's an AOTech Siren Gen 5. Same with the same information for the software version, the firmware versions, and the listed capabilities. Down at the bottom, you see the basic status is unknown. So because there's encryption, we can't figure out if this device is currently on or off or whatever other state it is. Now, since we skipped the configuration scan again, it shows that we skipped it, but in this case, it would show that that it was unknown because it's encrypted. So you might be asking yourself at this point, we're more than halfway into this presentation, well, what the hell does this have to do with breaking bulbs briskly? I'm sure that's what a lot of you came here for. So naturally, the EasyWave tool set is geared more towards reconnaissance. However, the messages used to control devices is very similar to the messages used just to interrogate the devices. So it's actually really easy to control these devices with software-defined radios. So naturally, once you have the ability to wirelessly control a device, the next question is, well, can I break something? And that's what we set out to do. We wanted to see, having access to a wireless automation system, how quickly can we break out something like industrial fluorescent bulbs or even residential CFLs.
So as he brings the slides back, I wanted to kind of zoom out. We've been looking at ZWave kind of through a soda straw. But ZWave, as you probably know, is not the only wireless smart energy protocol out there. We have a ton of solutions, all of them competing, and security is a hot mess, to use something my wife would say. So Wi-Fi, in the 2.4 gigahertz band, these protocols are fairly well understood, and there are tools in like Kali Linux for sniffing, Bluetooth, Zigbee. You have an outdated version of Killer Bee and Kali, but for the sub-gigahertz, like ZWave, Insteon and Lutron and these others, that 900 megahertz really helps the range of these devices. And so this has helped ZWave take the majority market share for the wireless security market. And so what we really wanted to help contribute to is the tool sets and the attack thinking for these sub-gigahertz protocols. So for what we did here was a case study. So these power switches are connected to something. No one just has them in their house for no reason. They're going to be used for Christmas lights. And so for the case study here, we look at fluorescent bulbs. Now, fluorescent lamps are in the home. They're in our hotel rooms. But more interestingly are the overhead lights in warehouses, factories, commercial office buildings. As smart energy keeps getting plugged, there's been a lot of push on how do you automate this stuff. And so even if it's not a wireless system, if it's a wired system that's not secure and we can get into it, we wanted to figure out how quickly can we physically damage something in the real world from the network. So how do you break a fluorescent lamp? You turn it off and you turn it on really quickly. But it's not as simple as turning it on and off 10 times a second and it'll be dead. It's actually a little bit tricky. So I'll talk about, there is a publication in the Journal of Industrial Technology back in 2011. And what they did is they took 35 compact fluorescent bulbs and they cycled them 2 seconds powered on, 8 seconds powered off, and they did this over and over again until they failed. And what they report is that it took about 7,300 cycles. And so if you're looking at time from an attack point of view, how quickly can I break them? That's about 20 hours. So that's pretty good. But there were two issues with that. One, it couldn't be done within a single night, and that was kind of our goal. And there's also a wide range. So what happens when you're breaking a fluorescent bulb? Every once in a while, it won't fail catastrophically. It'll just dim. And that dimming limits the current. It doesn't have the thermal stress, and it'll just survive for a long time. And that's how you get that long tail of 60 hours. So the research question looking forward is, how do we optimize this? How quickly is it possible to break fluorescent bulbs, both the compact fluorescents in the home and if you have an industrial control system that you've compromised, how fast can we break the industrial lights? So first thing you do, research, you got to replicate the results. So we took 8 bulbs. Couldn't justify this, so I had to buy them all out of pocket. But so we took 8 bulbs and we ran them until they failed. And the distribution looks really good compared to the journal, very consistent. On the left of these slides, you've got the box plot of the distro, and then on the right we have the mean. So very consistent. They were telling the truth. So we want to see, okay, so how quickly? So this is for the compact fluorescents. No one has looked at the industrial lightings as far as we could tell. So how fast can we break those? Well, the overhead lights in the industrial setting are not meant to be toggled on and off, like every time you go in and out of the room, like the compact fluorescents. So the mean time to failure is actually less than 10 hours. And here it looks like 6 hours or so. So what we did is we bought more bulbs and we broke those, and we tried different patterns. And so we tried having each of the cycle. So instead of 2 seconds on, 8 seconds off, we did 1 on, 4 off. And the performance improved. We were able to break them much faster. So we kept going. And like I kind of alluded to before, we tried cycling 10 times a second. But of course, without that thermal stress of the device turning on, the light heating up, and then you cooling down, without that thermal stress, the device will last for its intended life of 30,000 hours. So what we found the sweet spot to be was 1 second on, 3 seconds off. That's about as quickly as you can kill a fluorescent lamp when it comes to the overhead lamps. So, easily within half of a night, if the warehouse, no one's around, or the guy fell asleep, and the damage is cumulative. So if you perform these cycles, you will end up breaking these bulbs, and the cost of replacement can be substantial. And so going back to the compact fluorescents, we wanted to see, well, sure enough, this magic number of 1 second on, 3 seconds off significantly improved our attack performance. So we could break these in again, less than 9 hours. So that's how you break bulbs. All right, so in the takeaways here, as users, when you are connecting things in the real world to the network, you have to be mindful of what would happen if someone got into your system, because physical damage is now a possibility in this Internet of Things. And then read the manual, of course. All pages of it.
And the takeaways for the device manufacturers is just use encryption. If it's wireless, use encryption and make it the default, period. There's no reason not to. So EasyWave is available on GitHub at the URL listed there. So let the forking begin. Do you guys have any questions? So the question was, are these used for doors as well? So yes, there are quite a few ZWave enabled door locks on the market, and that's actually one of the big selling points for this protocol is the use of door locks. Usually in a smart home, that's one of the first things that people want to get. I have one in my house. They're actually pretty convenient. Any other questions? All right, thank you very much.